Okay, so we have been talking about fermions. And what I've been telling you is that even the free fermions was already interesting enough. We have this occupation number 1 up to the Fermi energy, if this is energy axis. Then by filling up the states up to the Fermi energy, even though this is a free particle, there is a pressure. You're working this out right now in the homework problem. And that would actually allow you to resist gravitational force in a star by this degeneracy pressure. And that's what we talked about as a white dwarf. We also talked about the fact that the metal, ordinary metal, actually looks like this. And this temperature is actually fairly high, thousands of kelvins. So at the room temperature, all the electrons in metal is really sort of filling up to the Fermi energy, and they are sort of rigid object. So that's, in some sense, the electrons are also metallic too. And then those electrons can move because going from here to there costs very little energy. So by applying some weak electric field, the electron starts to move because it costs little energy to do so. And to understand excitation spectrum of this system, we came up with an idea that you talk about whole and you talk about particle. And by defining, so this is just a review, we have all written this down. By defining a new creationization operator, which is actually the opposite. Did I use D or C? I forgot.
C.
D. So if I define this, when momentum is less than mu, and I don't change anything, when momentum is above the Fermi momentum, then this defines a new Hamiltonian, and you are verifying that the D operator satisfies the same the anti-commutation relations as the original B and B dagger creationization operators, so you're checking that now. Then in the end, you will find that this is now absolute squared sum over P, so that manifestly excitation energy is all positive. Then I'm asking you to also plot this. So original excitation energy of P squared over 2m minus mu looks like this. Because you have P squared 2m, that's a parabolic the curve, minus mu, so you bring the curve down, so that looks like this. So this area is where the energy looked negative, which was not very convenient thing to deal with. But now switching to this new operator, I flip the sign around, so this now looks like this. So the excitation energy is now positive manifestly for all momenta. And there's a special point here where the excitation energy is 0, which corresponds to the fact that going from slightly below this Fermi surface, this is called the Fermi surface. And we also have mentioned the name before. So this part is called the Fermi surface. Because if I actually draw this in 3 dimensions, let's see, I'm trying hard to actually make it happen. So it's a momentum space, Px, Py, Pz. And this radius is the Fermi momentum. That's where energy equals the chemical potential. And you have this surface of the sphere where energy is precisely chemical potential mu. So that's this Fermi surface. If I draw this way, the surface looks like one-dimensional. But if I draw it this way, it's clearly a surface, two-dimensional surface of a sphere. And if you're slightly below, like slightly inside the sphere, then you are somewhere here. And if you move the particle to slightly above, outside the sphere, then you bring the particle to over there. So in this case, you created a pair of a hole because I removed the electron just inside the sphere and created an electron just outside the sphere. So this is actually a whole particle pair. And creating this whole particle pair costs minimum energy, infinitesimal energy, because energy doesn't change very much from slightly inside to slightly outside the sphere. So that corresponds to the fact that excitation energy around this point is nearly zero. So the picture over there corresponds to create a hole here and create a particle there. Both of them have very little energy. That's why this system can be relatively easily excited, such as letting the electric current flow. So the fact that you have this large area Fermi surface is what makes a conductor a conductor. And so the electrons can freely go from slightly inside the sphere to slightly outside the sphere, and they can all flow in one direction if we apply an electric field. So that's how things like this can conduct electricity. So that's the idea. So that's what we talked about so far. So any questions about this? Yes?
For the unidirectional requirement, is it only for current flow?
Oh, directional requirement? So in this case, you apply electric field in one direction. So then the Fermi sphere shifts also in one direction. So having particle here basically corresponds to have created a particle, and here you don't have particle anymore, so that corresponds to the hole. So by shifting the entire Fermi sphere because of the applied magnetic field, you have created a bunch of electrons and holes in the system with very minimal energy. Okay? So that actually gives you direction, because most of the particles have positive momentum in this direction, so they flow all in one particular direction. Thanks for the question, Kay. Any other questions? Okay, then I also told you that this language of hole is actually very useful, because when you look at, for example, some large atoms, and you start to filling up all these electronic states, but if one of them is not filled, then it's much easier to think of this as a closed shell atom plus a hole. And that's the way you can very easily figure out the quantum number of various systems. So let me actually apply this to something you may not be familiar with. Maybe an example of nuclear physics. As you know, nucleus is a complicated system for a bunch of protons and neutrons. And unlike atoms, protons and neutrons are basically shoulder to shoulder. Each of them have finite size of the order of 0.8 times 10 to the minus 30 centimeters. And they have finite size because the proton is actually a bound state. It is made up of 3 quarks inside. Up, and down quarks. They are bound together by a very strong force, much stronger than any other forces we know. And that's why it's called very creative name, strong force, or strong interaction. So this is actually meant to be a proper noun. It is not a strong interaction, but it is actually the strong interaction that binds the quarks inside proton. And you can never see a quark in an isolated fashion. That's the idea. And so because it's a bound state, it doesn't have a finite size of the order of 0.8 and 10 to the minus 13 centimeters. So it's actually tiny. So if you think of the atom as big as a ballpark, then the size of a nucleus is basically a baseball with a pitcher's mound. So incredibly tiny, if you think about it. And that's how small the protons and neutrons are. And those small things are sort of bound together in the nuclei shoulder to shoulder. And the reason why they bind together is actually a very long story. I don't get into it. But you can actually sort of come up with a model called shell model. A very empirical model that you assume the protons and neutrons are basically inside some kind of a spherical potential like this one. And you start to fill these energy levels in. Then inside this potential, lowest energy level, so this sort of like looks like a harmonic oscillator to some extent, if you actually expand it like this. But of course you flatten out the distance range of the potential. But the bottom potential is really a regular 1s state, just like what you expect in 3D-dimensional harmonic oscillator. So this is roughly speaking 3D harmonic oscillator. In 1s state, of course, can have both spin up and spin down. And you can fill in both proton and neutron. Each of them spin up and spin down. And if you fill all of these states in 1s state, then you have 2 protons and 2 neutrons. And that is nothing but an alpha particle or helium-4 nucleus. So given that this helium-4 nucleus fills up all of these lowest energy states, this is particularly stable because that's the analogous to noble gas in chemistry. So the same idea of filling up to the energy, the Fermi energy, works in nuclear physics as well. And once you actually fill up with a big gap in between, then it's not easy to excite the particle from here to there because of the energy gap. So the state you have becomes particularly stable. In the case of metal, you have this big Fermi surface. So just by preserving a system with a tiny electric field, everything starts to move because it costs very little energy to let them move. But if you have a big gap from the state you occupy and state you are not occupying, then it takes a lot of energy to create an excited state, which means that the state tends to stay in the ground state, and that's why it's very stable. If you just kick it, nothing would happen to it, because it would really require a lot of energy to get the system excited. So that's why alpha particle is very stable. That's why big nucleus tends to spit out alpha particle as a whole instead of individual protons and neutrons, hence nuclear alpha decay, as I'm sure you have learned in freshman physics class. Knowing that this is a particular stable state, you can create a hole in this, like removing one neutron. So you remove one neutron, that becomes helium-3. And this is a 3-body system, which looks kind of complicated. But once again, you lose the language of the hole here. You have this stable closed shell nucleus. You have one whole anti-neutron in a 1s state. And given 1s, and spin is 1/2, L is 0, spin is 1/2, so the J has to be 1/2 by addition of angular momenta. So you immediately know that helium-3 nucleus has spin 1/2, right? So this is how the language hole is actually useful even when you go to nuclear physics. And these very stable closed shell nuclei are called magic numbers. So fitting 2 for proton and 2 for neutron is one of the magic numbers. 10 is also a magic number. 20 is also a magic number. So if you look at helium-4, this is 2 for proton, 2 for nucleon, that's doubly magic. That's the name people use in nuclear physics. This nucleus is doubly magic because you have 2 magic numbers, both for neutrons and protons. For the case of 10, I forgot what that is. No, this is actually 8, sorry. This is oxygen 16, that's doubly magic. And then for 20, that's calcium 40. So this way you can understand some very stable nuclei, and then you can use the language of both creating a particle as a particle or removing a particle as a whole, and by combining a few numbers of particles and wholes, you can understand various properties for nuclei as well. So that's actually useful. So obviously I'm not getting too much detail here, but any questions about the general idea? Is it okay? So now comes the interesting question. Suppose you have helium-3 instead of helium-4, and helium atoms is also closed shell in terms of electrons, because you fill up the 1s orbital of electron by 2 electrons spin up and down. So this is close to doubly magic, except that you have a hole of neutron. Electrons are closed shell. So this whole system is basically closed shell minus a neutron. Then you immediately know that even the helium atom as a whole, there's spin 1/2. Right? Electron is a closed shell, so overall it's totally spherical, it doesn't have orbital or angular momentum. Helium-3 nucleus is a doubly magic nucleus plus the hole of neutrons in 1s state, which has angular momentum 1/2. You immediately know the whole atom has the J equal 1/2 as the total angular momentum. You don't need to worry about adding 3 particles in here and 4, 5 to build up the wave function. Just by drawing the picture, you know already the helium-3 atom is spin 1/2. And because it's spin 1/2, this is actually a fermion. And this is something we'll come back and talk about when we get to relativistic quantum field theory. In non-relativistic QFT, the Schrödinger theory we talked about, you could have chosen Fermi statistics or Bose statistics by choosing the field to be Grassmann odd or Grassmann even, no matter what spin that field might carry. So there was no connection between the two. But when you go to relativistic QFT, that would be coming later, so you don't need to worry about it right now. There is a complete one-to-one connection between integer spin, which has to be a photon, and half-up spin, which has to be a fermion. And I don't think I can get into the proof of this theorem, but this is actually a proven theorem called spin statistics theorem. So knowing that total spin is half-odd, which is the case for helium-3 atom, we know it's fermion. So helium-3 atom is a fermion. I should go actually over there. Sorry about that. So now we start to think about this whole interesting problem. Suppose we have a bunch of these helium-3 atoms. Then go to very cold temperature, what would happen to it? What we have studied for helium-4, or in general, both bosonic atoms. And when they go to low temperature, you have the degree wavelength of each particle become longer and longer, and eventually the whole thing starts to behave like a wave. That was the Bose-Einstein condensate. We talked quite a bit about this. Now the question is, if you do the same thing with helium-3 instead, what would happen to it? And here, then you have to put in some interactions among them. So we looked at this form of Hamiltonian for the boson before. So this creates this annihilates particles of momentum k and L. So they come in, they are annihilated, but then you create particles of momentum p and q. So this describes a process that these particles can scatter among each other. And the total momentum is conserved because k plus L is the same as p plus q. So initial state momentum and final state momentum are the same. And I told you that you can actually derive this form by starting with this Lagrangian and Schrödinger field theory and going to the momentum space. And you can work out this form of the interaction. And in the case of fermion, to be completely honest, because of the theorem, you have to introduce spin degrees of freedom. But I'm not going to do it just because it's so that it becomes everything a little bit more complicated. So I pretend we can deal with this as a fermion without thinking about spins. So then you have this kind of Lagrangian. Then you ask the question, could fermions also lead to some kind of condensate again? In the case of the boson, the condensate, the big condensate was obviously the zero momentum mode. As a function of momentum, occupation number was macroscopic for zero momentum. Then you have some behavior like this one, and around the chemical potential, occupation number becomes extremely small. So that was the behavior we had for boson. So we said the creation and annihilation operator of the zero momentum mode is of the order of the square root n, where n is the macroscopic number of particles. Then you look at the important pieces in the Hamiltonian, and then try to diagonalize the Hamiltonian using Bogoliubov transformation. So that's what the previous book was about. Sandro?
Yes, I have a question. When I think of a scattering, I usually think of like two particles interacting with each other in the same place in space. But in this case, we know the momenta, so what's the meaning of like a place in space?
Well, it turns out that this is actually the same thing, and there may be a factor of L cube or something like this. So if we actually start with the Lagrangian, we have seen many times by now. And then all the fields are at the same space position. So this interaction is totally local.
Isn't it always zero for fermions?
Yeah, so that's why you actually have to put in spin. So
Okay.
that's a very smart thing to point out. So when you strictly think about fermion with no spins, then I'm multiplying 2 psi of x twice. And that's identically zero.
Exactly.
So to do everything more correctly, what I should do is to put in the fermion field for spin up, fermion field spin down. Then I'm allowed to multiply them on top of each other at the same position because they are different fields.
Okay, so in this case, the interaction occurs when two particles with different spin are like in the same position.
That's right.
Okay, fair enough.
So then I should have written the
Makes sense.
interaction term of the Lagrangian this way. Then this doesn't vanish anymore. And then if you go to momentum space, this is basically the delta function, and the Fourier transform delta function is constant in momentum. So that's why this is just an overall constant that doesn't depend on momentum of the particles involved.
Okay.
And if this interaction is long range, then there is a difference between two positions. And I have to integrate by some interaction which is long ranged. Then I have two integrals, x and y integrals. You have seen this expression for the boson field before, and you're doing the same thing now for fermions, except that they are now anti-commuting, And to be sure, you also have to break the spin degrees of freedom. And we're not going to actually get into this for now. But the idea is that when you have long-range potential, what comes in here will be the Fourier transform of this potential. And the Fourier transform of function in general is a function of the momentum. So this coefficient would also depend on PQKL in general. So in general, this would be the momentum which depends on P plus Q, which is the same thing as K plus L. So this is the Fourier transform of this long-range potential to the momentum space, which now depends on the external momenta, P and Q, and K and L as a result. So that's the thing I'm supposed to put in here. But when I take the approximation that this is local, given my delta function, then the Fourier transform delta function is a constant. That's why I'm just writing down a constant in front of these creationalization operators.
Okay.
Then if you, again, want to be sure that you have to spin degrees of freedom, you have to put in spin up and spin down over here. Excellent question. Yes?
Shouldn't there be a sum over like?
I'm not sure I can hear you.
Is there a sum over K, L, and P?
There's a sum over PQ and KL. Yes. That's another important question, so thank you for asking that. And this one obviously is also sum over P. Thank you. Any other questions? Okay, so in the case of boson, you know what to do by now. So because there's a macroscopic occupation number for zero momentum, we could have pretended that zero momentum part is just a coherent state. Annihilation operator is an eigenstate. Eigenvalue is basically given by square root of the number of particles in the system. So you replace zero momentum creationalization operator by numbers. Then by putting those numbers in, you have found the Hamiltonian that look like A dagger A, but also AA by letting these two be zero momentum, or A dagger by putting these two to be in zero momentum both. So you have this weird Hamiltonian that has A dagger A, but also AA and A dagger. And you have learned by using Bogoliubov transformation, you can diagonalize it and read off the excitation energy, and that really beautifully agree with the experimental data that shows linear and quadratic behavior as a function of momentum. That's the Bogoliubov spectrum. We derived in class using just classical field. And in retrospect, I hope you appreciate that was way easier than dealing with futzing around this Bogoliubov transformation of the operators. So the classical field theory, in some sense, is a better description than operators, but nonetheless, it was really assuming that you got exactly the same answer both ways. So that's what we have learned in the case of bosons. Now, thinking about fermions, clearly this is not the right picture, because you cannot put macroscopic number of fermions in zero momentum, because that would violate the Fermi statistics. So that's not what's going on. However, when I think of breaking a particle with momentum L, then if I pick this Q and K to be the same, then I'm summing over Q and K, I take them to be the same, B dagger B, summed over all momenta, which means that's the total number of particles in the system. So this combination, summed over Q and K, can still be macroscopic. So unlike the boson, it's not a coherent state, obviously, because you can put in more than one particle in the same zero momentum state. But the pair, K and K here, summed up all K, is once again the total number of particles in the system. So this combination can be macroscopic. So we can try to do a very similar approximation of feeding this Hamiltonian, PQKL. This is the irrational Hamiltonian. some coefficient. So if I take Q and K to be the same, then sum over Q, B dash of Q, BQ, is nothing but the foldable particles. So instead of replacing 1B by square root of n, 1B dagger by square root of n, B dagger B summed over Q can still be macroscopic. So that gives one term that looks like big N, B dagger P, and according to momentum conservation, if Q and K are the same, P and L have to be the same, so this is to B of P. So we get a term like that. So that's normal looking Hamiltonian, and of course we're okay with that. But once again, we can have some kind of condensate where the pair of particles, Pn minus P, can have non-zero expectation value. So unlike the Bose-Einstein condensate, this is a pairwise condensate. And P and minus P have to be really opposite to each other because the total momentum carried by this operator is zero momentum. And assuming that the ground state is homogeneous, which means no dependence on space. No dependence on space is zero momentum, right, in quantum mechanics. So assuming that ground state carries no momentum, the only combination that could have non-zero expectation value is the combination that carries no overall momentum. So this is a possible condensate consistent with momentum conservation. So if this kind of condensate exists, again sum over all momentum modes, then this piece, and we're setting these to be the same opposite momentum, P and minus P, summed over P and Q, which is sum over P now, could have a large number, so that you may have to keep a term which looks like BB. But again, thanks to momentum conservation, if P and Q cancel against each other, K and KL have to also cancel against each other. So then you find a term that looks like BK, B minus K, with a coefficient that depends on the size of the condensate. So let me call this delta. Delta has a dimension of energy. And if you have a term like this, of course, there has to be complex conjugate of this. And here you have to be careful that when you take Hermitian conjugate of this operator, this Hermitian conjugate goes over here. This Hermitian conjugate goes to the right now, according to the usual rule. If you're sloppy, you may say, well, order doesn't matter because the B dagger should commute with each other. They don't. They anti-commute. So if you change the order, you get an extra minus sign. So you have to start paying attention to those little details about anti-commuting numbers. But nonetheless, idea is still the same. So just like what we have done with the boson, you can replace B dagger B by big N, BB, whose size we don't know at this moment, but just assuming that that exists, which may be also macroscopic, but comparable size, you have a Hamiltonian to non-zero momentum together with this delta in it. And if you work this thing out, once again, the coefficient of this becomes mu that cancel this negative mu. So this piece here ends up being p squared over 2m plus mu. So at the end of the day, you're looking at a Hamiltonian that looks like B dagger B, which is the normal Hamiltonian we love and know, but also additional terms that look like B and B dagger. And you once again have the same problem we had before for bosons to diagonalize the Hamiltonian. So here you're talking about this pairwise condensate. So when you have this Fermi surface in momentum space, it turns out that this kind of pairwise condensate is the largest when the particles are close to Fermi surface. And here you have P, you have minus P. Then you could have this pairwise condensate, and you'll see this in a moment. And as a result, occupation number doesn't look like this anymore, but it starts to look like the color swap. I don't see one. No, there isn't. So let me use the dashed line instead. It's going to look something like this. So you see something is interesting going on near the Fermi surface. And this is the region where this pairwise condensate is actually the largest. This is the size of this BB condensate. And then you find that this is actually another state, which is similar to Bose-Einstein condensate, and number is now uncertain. Because here you're taking the linear combination of particle and the whole. Sounds like a really weird notion, but that's what we're doing. And your state, again, has no definite number eigenvalue, like a coherent state. And the way you can describe this ground state is something you can guess. In the case of boson, you acted exponentiated creation operator on the ground state, at vacuum state, to create a coherent state. Now in the case of fermion, this is zero momentum mode. You can't do this because you can't fill state more than one time. But instead, what you can do in putting this creation operator of the pairwise creation operator, sum over P, and F may depend on P, so it should have been inside the sum instead, and add this on the ground state. Then what you see is for individual momentum mode, I have linear combination of FP, A diagonal P, A diagonal minus P, and somewhere the exponent is a product of the exponential. So what you see is that for individual momentum mode, I'm adding state with no particles and state with one particle for momentum P, one particle for negative momentum minus P. And it stops here because I can't put in any more particles. So you're putting linear combination between states with different occupation numbers. And that's as close as you can get to the coherent state of the boson. And I'll show you more details about how this works in a moment, but I'm just trying to give you a big picture that even with the fermions, you have something closely resembling Bose-Einstein condensate that can exhibit coherence because your ground state has uncertain n, so that correspondingly, phase is somewhat well defined, which is a sign of coherence. And as a result, you can have similar phenomena like what you have seen in BEC, like the lattice of vortices. And this is actually a system made of, I forgot which one, I think this was lithium-6. So lithium-6, the nucleus has 3 protons and 3 neutrons. So that's a boson. But lithium is an alkali element, so you have 3 electrons. So everything is 3. But 3 electrons would give you at least 1 spin left. So you have 1 is orbital occupied, 2s was 1 electron in it. So obviously you have spin 1/2 for the entire atom, okay? And if you create a very cold gas of lithium-6, you can see these the lattice of vortices, and that is a manifestation of the coherence of the gas made of fermions. So you're going to pass this out. And just in case you are interested in the 2 limits here, this BCS limit on the right is what we are looking at right now. I come back in and tell you what this BEC limit is about in a moment. So that's sort of the big picture, and I will try to fill in the details. But any questions at this stage? Yes, Sarah?
I don't quite understand why we can only go up to just 2 terms. I thought there could be infinite amount of momentum.
Can you speak up?
Why do we have just 2 terms for linear combination instead of like infinite number of momentum?
So for each momentum mode, if I expand this exponential, I get this thing squared, this thing cubed, and so on. But the minute you square this thing, then I have a dagger b twice, and that's identically 0. A dagger minus b twice, that's identically 0. The only way this thing squared doesn't vanish is when you multiply this combination in combination with different momentum. So you create this linear combination for every momentum and multiply them on top of each other, so that in the end you have macroscopic condensate. But for individual p, the size of a condensate is only order 1. So you get the macroscopic number only because you sum up this kind of pairwise condensate for all momentum modes. And that's the difference in fermions. Because you cannot use same momentum mode over and over again to create a macroscopic number, because you can occupy the state more than once. But if you have this pairwise condensate for each momentum, that's order 1. But if that pairwise condensate exists for all momentum modes, then they can accumulate to become a big number at the end of the day. And that's the piece that will lead to this term in the Hamiltonian, which I call delta.
So does that p raised under 1s, that's, are we summing over the p?
Yes. So if you look at this combination sums of p, then you sum over this overlap, that's of the order of f, I told you. It turns out that it's actually a cosine and sine, like Paschen sinh for the case of boson. So this actually ends up being sine 2 theta. Then you sum the sine 2 theta over all momentum modes inside this original Hamiltonian, where I replace this BE with an opposite momentum summed over PQ by a macroscopic number, because it's summed over all momentum modes. Does that make sense? Okay. Any other questions? Yes, I
was wondering, you said that the number of particles is uncertain, right?
Right.
But isn't it just the integral over the graph?
Integral over the graph. So here what we mean is that if you compute, for example, the uncertainty number, you compute something like this.
Yes.
And if the state, ground state, is an eigenstate of the number operator, then this number operator just becomes the eigenvalue squared.
Mm-hmm.
This one is also eigenvalue twice. So they precisely cancel. So there's no uncertainty. So if delta n is non-zero instead, that corresponds to ground state not being the eigenstate of the number operator. Therefore, you can have non-zero delta n only if your ground state has a linear combination of different number of particles in it. So if this is actually total number but that's fixed with no uncertainty, you can never have delta n finite. Therefore, you can never have delta theta finite and no coherence.
So the curve that you brought with the dashed line there is impossible to be found.
Well, so you can compute the total number as an expectation value.
Okay,
But this is not the eigenstate of the number
Okay.
operator, which you can see here.
Yeah.
This is a linear superposition of particle state with no particle and two particles. And you do the same thing for other momentum modes. So that in the end, you have macroscopic number of particles in the system. But the point here is that this is not an eigenstate of the number operator. And this is the state which is called the BCS state, which corresponds to the name of the people, Bondi, Cooper, and Schrieffer. And this state was proposed in a way of trying to understand a superconductor. So when you cool some kind of metal like an niobium to very low temperature, then it completely loses the electrical resistivity. And electric current can flow without any loss, which would be really great for power grid. I think I talked about that before. So that's the phenomenon where electric current can flow without resistivity. So that's sort of electric version of superfluid. And so that was the reason why they invented this weird wave function. But now that we can also create this kind of system with the cold gas of atoms, you can cool, for example, I mentioned the lithium-6 atoms on this picture, and then cool it down to very low temperature, and they start to exhibit superfluidity in that case. And that is also described by this BCS state. So the BCS state is no longer just confined to the superconductor, but is now applied to other systems of very cold fermions. And even for the cold gas atoms, you can create this BCS state, and then hence observe this kind of coherent phenomena. Thanks for asking that question, Alessandro. Any other questions? Yes?
Whether delta phi is a negative.
What is negative?
The delta phi, delta theta.
Delta theta. Sorry, this is not negative. It's meant to be finite. Sorry. Yeah, thank you for the question too. Any other questions? Okay, so now that I hope you got some picture of what's going on, let us be a little more concrete. So, at the end of the day, you have a Hamiltonian. By picking up a particular momentum mode, that looks something like and this E naught is P squared 2m plus mu. Then I have delta. That looks like this. In higher orders, suppressed by 1 over square root a. And we've been there before, so we have seen this kind of Hamiltonian for bosons, and found out this Bogoliubov transformation with diagonalized Hamiltonian. We have to be a little bit different because they are anti-commute. So what you do in the end is define the following linear combination. CP, and I'm actually dropping this vector symbol just for the simplicity. So just like in the case of the boson, these are linear combinations of creation and annihilation operators. Annihilation and creation, creation and annihilation, weighted by sine and cosine instead of sinh and cos. And it turns out that this preserves canonical anti-commutation relation. Like this one. And C's need to commute. And C daggers also anti-commute. So by doing this transformation, I now define a new creation annihilation operators. They qualify to be called a creation annihilation operator because they satisfy the same anti-commutation relations. And using this C and C dagger, we want to write this Hamiltonian as E of P times C dagger P CP plus constant. So if you manage to find right theta, so that this original Hamiltonian turns into this form, then you know what you're talking about. Your ground state is the state that is annihilated by the annihilation operator here. And assuming that E of P is positive, we make sure of this. If it's annihilated, then you can't lower energy anymore, hence that's the ground state. And when you create one C, then that raises the energy, that's an excited state. So if you manage to write the Hamiltonian in this form, you learn both what the ground state should be by the condition that is annihilated by COP annihilation operator, and what the excitation energies are when you create one or two these particles. So that's the aim. So you start with this Hamiltonian, you carry out this Bogoliubov transformation, and find the right angle so that Hamiltonian looks like this in the end. No CC, C dagger pieces. So these pieces are not there. And once you have done so, then you know everything what you want to know, namely what the ground state is, by the condition that it's annihilated by the CP operator, and what the excitation energy is, by working out this E as a function of momentum. So that's the idea, and which is exactly the same thing we have done with the boson last week. Any questions about what we're trying to do here?
There is a sum, right, over all these.
Yeah, so this is this one is included. So if you want equal, this has to be sum over P.
And then why do we need like both the positive P and the negative P?
I'm sorry?
Then why do we need?
That should be sum over P on positive, I think.
Yeah, so I have to do this.
Okay.
So only half of the momentum space. Yeah, to avoid double counting. That's right. Any other questions? Everything okay? All right. So then we try to find this the angle. But the first thing first, we would like to make sure that this is indeed correct. And this depends on P. And C dagger Q. And when you look at the pieces that do not anti-commute, it's only the piece where B and B dagger come in, and when the two momenta are the same. So this times this, delta PQ, times cosine cosine, because P and Q end up being the same. This is cosine squared. And B dagger B, this combination again don't anti-commute. and give you 1. Only when P and Q are the same. Then I have sine squared. And P and Q are the same, it's actually squared. Now you see cosine squared plus sine squared is 1, and therefore this is delta PQ. And the difference for the boson is that when you had a boson, this was a commutator. The commutator. B dagger gives you 1, that's fine. But B dagger B gives you -1. So you get a minus sign here. That's why we needed cosh and sinh. Cosh squared minus sinh squared is 1. And that was what we have done with the boson. But for the fermions, we have this anti-commutation relation instead. So B dagger B piece is 1 instead of -1. That's why this is a plus sign here. To keep it 1, what you need is cosine and sine instead of cosh and sinh. That's why we're using cosine and sine to work out the Bogoliubov transformation. And anti-commutator between two annihilation operators. And looking for the B and B dagger piece, B and B dagger, sine and cosine. And that's only when P and minus Q are the same. Now I'm worried that this might actually not cancel. So there's something wrong. B dagger, cosine sine. B dagger B, that's also sine cosine. No, they seem to add up. I must have done some mistake here. Ah. Minus B is B, B minus Yes. Sorry, I did this minus sign which I forgot. So only together with this minus sign, things work out. So for CP, I get linear combination with plus sign. C minus B, I get linear combination with minus sign. Another way of saying is that you might say C theta of P is minus theta of minus B to get this minus sign if you like. It's the same thing. And then it turns out that this second one over here has a minus sign, and they cancel. Sorry, I got a little confused, but this is the way, again, things work out. And the conjugate of this is the same deal, so that's something I need to check again. So that's how we know that this new C and C dagger creationalization operators qualify to be understood as a creationalization operator because they satisfy the same anti-commutation relations. Once you do, starting from this Hamiltonian, by plugging that linear combination in here, by solving for B in view of C, to rewrite everything in terms of C creationalization operators, and work out the coefficients, collect the coefficients of CC, which you don't want, and set it to 0, that gives you a condition what this theta angle should be. And once you actually use this angle, this Hamiltonian turns into this. And you have diagonalized the Hamiltonian, you have simple interpretation of what's going on. Now together with this delta, remembering that this E naught used to have the spectrum that look like this, now went to 0. But now there's this delta squared inside. If you set delta to 0, E naught squared is this. But together with delta, it looks like that. So it never goes all the way to 0, which means there's the minimum energy you need to excite the system. And this is what is called the gap. And now that there is a gap, you can apply the Landau's criteria, if you remember, that if you want to make sure that any macroscopic obstacle would not create microscopic excitations to lose the energy of flow into microscopic stations, you wanted to see if EP minus BP crosses 0. That was the Landau's condition, which means I draw a linear line proportional to velocity of the flow to see if they cross. And now you see it doesn't, up to the velocity that just touches this bottom of this gap. And when the velocity is even faster, then you can start creating microscopic stations so that the energy of the flow, macroscopic flow, can be lost into excitation at the microscopic level. And that's a dissipation process that causes friction, and that will lead to resistivity. But if you're below this critical velocity, then there is no solution that satisfies energy momentum conservation. So again, you can have a macroscopic flow that doesn't lead to dissipation. And hence, this becomes a superfluid. And people have done experiment, not with this helium-3 or lithium-6 fermion, but with the superconductor in the material. Then they let the electric current of the superfluid is called supercurrent for obvious reason, and they actually created a system where they observe supercurrent keep flowing well more than a year. So it really doesn't dissipate. The viscosity or resistivity is really, really 0, so that current keeps flowing. So this kind of superfluid or supercurrent with charge really does happen. And the picture you have seen in these vortices is also that around each of these vortex, you have this circulation you have computed before, h over m. And each of the superfluid keeps circling around each of these dots. And because there's no resistivity, you can have this kind of situation happening, and you can observe this for a long period of time. So this is also manifestation of no dissipation, no viscosity, no resistivity. So this gap is what really makes that possible. And whenever you look at any literature in superconductor, they always talk about this gap, because this really tells you how robust the system is, because you need certain temperature to start exciting this gap. A gap is a thing that can cause viscosity and resistivity. So this basically sets the overall energy scale of the problem, where this kind of transition can happen from a system with no resistivity and a system with resistivity. That's a normal metal. So this gap is a very important number. And as we have seen, this gap comes from this interaction term where you replaced BB by a condensate. So if there is a gap, that's an experimental evidence that the BB condensate exists. Again, it sounds very strange, that you can annihilate the ground state twice, and you are still in the ground state. But because the ground state is already a linear combination of states occupied and states not occupied, even if you annihilate these occupied portions of state twice, you remove the pair, but your ground state still has a piece that doesn't have occupation to begin with, so that gives you the overlap between the two. So that's how this gap is now there. But one thing you might have noticed is that I assumed this BB condensates exist. Assumed. And summed it over all the momentum modes to give you a macroscopic number in the end. But now that we worked out the ground state, then you should be able to check that this is indeed non-zero. And so what's going on here is that now your ground state is annihilated by Cp. You can work out what the ground state looks like. I think this cotangent theorem. Let me see if this is going. I didn't write it actually on my slide, so I have to check. If I add VP on this, I anti-commuted this one, and I get maybe this tangent. The cosine times tangent is sine. If I add this one on it, I keep it from here, that's sine, so that they can cancel. So let me try this. So VP cosine theta plus B diagonal minus B sine theta, acting on this thing. So if I take BP and use this portion 1, then annihilation operator goes straight to this vacuum state, so that's 0. But when I have this BP acting on the second part of the ground state, I use anti-commutator of BP and BB diagonal to get a 1. So then I can go from BB dagger down to B dagger B. And once B is on this side, that would anti-commute with B dagger minus B, so I get the BP act straight on the ground state again, that gives me 0. So the only piece that remains is the BB dagger anti-commutator, that's 1 with cosine theta, the tangent theta. So that's the piece coming from BP, and I made it minus sign here. And this B dagger minus B, together with this 1, gives me B dagger minus B acting on the vacuum state. And that is sine theta. Because I used 1, there's no other angles. This B dagger minus B acts on this state instead. I already have B minus B dagger created. I'm doing this once again. So that's identically 0 because it's a fermion. So this piece doesn't contribute. So in the end, I get this combination, and clearly I made a side mistake. I should have chosen this state instead. Then these two they cancel. So that's the ground state. So for each momentum mode, this linear combination I mentioned to you earlier, based on the analogy, the boson-Einstein condensate, but really doesn't turn out to be the correct ground state for this BCS system. which is now annihilated by this excitation, C of P. Does that make sense? Well, if you do the algebra, it's actually not that difficult, so I hope you will actually get it in the end. So then the C of P really does tell you what the ground state looks like. And as we guessed, it is sort of the coherent state of this pairwise creation operator. But pairs creation operator twice is again identically 0, so it truncates at the first order pairwise creation operator. So that's why it stops here. And using this pairwise condensate, you can really compute then this BB expectation value, because if you use this ground state and compute GS BP, B minus P, ground state, this pairwise state would annihilate this B dagger, B dagger. I get tangent, and that would give me state 1, which is inside this ground state. Then you find that this is proportional to tangent theta, which is non-zero. So it's self-consistent. So we assume this pairwise condensate exists, then worked out the Hamiltonian, worked out the ground state, and using that ground state, we compute the pairwise condensate, and indeed see that it is non-zero. So that's how you see the consistency of this approximation. And also now that we know this cosine 2 theta in sine 2 theta, you can compute this size of the condensate. The actually best thing to look at is actually sine squared theta. When energy is much less than delta, then this is basically delta minus 0 over delta, so that's 1. When E naught is much bigger than delta, you can ignore delta, so they cancel, so it goes to 0. So you should find a function that looks like delta as a function of E naught. This is sine squared theta. And remember, sine theta is the coefficient of this wrong operator in a Bogoliubov transformation. So what it means is that when you are in a very low energy range, sine theta becomes almost 1, cosine theta becomes 0, which means your annihilation operator is more than just a creation operator. And that's the thing we did with Paul. So the creation of levels well below the Fermi surface is the Hall operator, which we knew all along. So around here, you're talking about Hall. But when you go to large energy, then sine squared almost vanishes. That's the case when there's no difference between C annihilation operator and B annihilation operator. Then you're talking about particles. And this C operator, which is called Bogolon, it's a funny name. You know, according to Bogoliubov, this is a kind of particle protected by Bogoliubov, so it's called a Bogolon. And this Bogolon smoothly interpolates between the Hall and particle near the Fermi surface. And that's how you can diagonalize this self-interacting fermion system, it turns out. Yes?
Yeah, there are 2 missing over there. The
What
last
is
term
missing?
of the sine square.
There's a factor of 2?
Yeah, but if that's a 2, then the maximum of the should be a half.
Sorry?
If the if we set the E0 to 0,
E0 to 0, okay?
then it's a half, right?
Oh, okay.
So the maximum of the sine square is a half. And probably the cosine 2 theta is wrong. I don't know. Something,
right.
there is something wrong with the algebra.
No, I didn't write it down. You're right about it. I must have screwed something up here.
Isn't it like 2 times the root of E naught squared plus delta squared?
Yeah, it has to be. Oh wait.
Well, yeah.
Okay, well, I
Isn't it-
come back and fix this on Friday. Sorry, I can't do that right on the fly. But I hope you get the idea that there's an interpolation between a whole and particle, and that's how you can get this real wave function, which is the BCS state, that has a linear superposition of state without the pair and with the pair. And you see the self-consistency of this assumption of this pairwise condensate, and that's how the fermionic, the condensate actually works. And finally, coming back to this picture, if you dial interactions among fermions, and if you have the strong attractive force between 2 fermions, let's say in this case lithium-6 atoms, the 2 lithium-6 atoms may bind together to form a molecule. A bound state of 4 fermions would be boson. So when you have a strong attractive force, then you can have this molecule as a boson forming a BEC, boson-Einstein condensate. On the other hand, when attractive force is weak or even repulsive, then you can go through this and find this BCS state, but they are related just by dialing the strength of interaction. So it turns out that there's a continuous change from this limit where you have a Bose-Einstein condensate of molecules versus pairwise condensate of the fermions. And that's a behavior called BEC, which is the limit where you have strong attractive force, well, atoms form the bosonic molecule first and the molecules condense, that's this limit, to BCS, where you have weak interaction among the atoms, each atom being a fermion, but you have this pairwise condensate, and you can have continuous change from one limit to another, and you don't see much changes happening. And that's why this is called a crossover. And when you change your parameter, and if you see a drastic change somewhere between, you're talking about a phase transition. Like you change the temperature of water, you go through a drastic change from liquid water to vapor. That's a drastic change, that's a phase transition. But there's no drastic change in this case, so as you change the parameter, you say that's a crossover from one limit to another, hence BEC, BCS crossover. So that's, you can sort of put everything in a big picture. In the case of boson, you can have Bose-Einstein condensate with the repulsive force at very low temperature. When you have fermion, you have sort of spectrum of possibilities. When you have weak interaction among them, you could have this pairwise condensate of BCS state. When you have a strong attractive force, fermions combine into bound states, and bound states as a boson condense to become Bose-Einstein condensate, and there is a continuum in between of the BCS-BEC crossover. So let me write this one down. So when you have strong, then you have these molecules, each of them boson, forming BEC. When that is weak, you can have these particles with opposite momenta near the Fermi surface, and they have this pairwise condensate, that's BCS. And you have continuous connected between the two limits, called crossover. And that's indeed what is seen in the experiment. Yes?
When you're mentioning a crossover, are you talking about these two condensates are exactly the same?
So it's very difficult to describe. So here we have written down the BCS, the wave function. We know quantitatively what we are talking about. Here, you assume that this boson molecule is already a point particle. Then you know how to write down your wave function using the coherence state. In between, you don't know exactly what you're talking about, but qualitatively, they should represent the same physics. So somehow they must be connected. And that's what is shown by this experiment. So if you want me to write a wave function right here, I don't know how to do it.
But the two ends of the spectrum, are they exactly the same? If we're not considering the process of the transition?
No, they are not the same, because this is the BEC limit. So your excitation spectrum, Bogoliubov spectrum, looks like this with a linear rise. Here you have the BCS state. Your spectrum looks like this, as we just talked about.
Okay,
So here there's a gap, here there isn't.
Okay, then the crossover is not technically or rigorously processing, proceeding from one phase and then to somewhat we don't know about, and then go back to this phase. It's two different phases.
Yes.
Okay.
But they are continuously connected. So now if you're looking at these two limits, you may conclude that they look like different phases. There must be phase transfer in between. But what I'm saying here is that there isn't. They are continuously connected, and it's a crossover. Okay? This is the end of the class. Any other questions? So I will fix that factor 2 on Friday. I apologize. No other questions? Yes, sorry.
What determines the strength of the particle interaction?
I'm sorry?
What determines the interaction strength?
I couldn't hear you.
What determines the interaction?
What is the interaction strength?
Yeah, the stronger interaction determines the EC.
So strong interaction in this case means that typical kinetic energy of each of the molecules is much smaller compared to the binding energy of the two atoms into a molecule. Any other questions? That's an excellent question, Sarah. Anything else? Okay, and how are the midterms going in general? No, then how are other midterms going? Not ours. Okay? Okay, you must be having busy time.
How did it go, by the way?
Sorry?
How did it go?
I don't know.
Yes, go ahead.
Yeah.
We saw it as 3 pi.